Alright, so this video discussion is just the continuation on the first discussion that we have, specifically on the lesson 1 topic, which is rock forming minerals, which has those topics of physical properties. Now let us proceed to chemical properties of minerals. Now all minerals can be represented by a chemical formula which presents the proportions of atoms that constitute them. For example, the mineral quartz has a chemical formula of silicon and oxygen. Now, its crystal structure is a continuous framework of silicon-oxygen tetrahedra. The chemical properties of minerals depend on their chemical formula and crystal structure. Solubility and melting point are chemical properties commonly used to describe a mineral. Solubility refers to the ability of a substance to dissolve in a solvent at a specified temperature. For example, biotite, a mineral commonly found in igneous rocks, is soluble in both acid and base solutions. The dissolution releases the loosely bound potassium ions in the mineral. Now, same also with, for example, a tablespoon of sugar. Then you will dissolve it in a hot glass of water. So that is solubility. It is the ability of a substance to dissolve in a solvent at a specified temperature. Now, next to solubility that pertains to chemical properties of minerals is melting point. So, melting point refers to the temperature in which solid turns into liquid. Minerals composed of atoms that are tightly bonded within the crystal structure have high melting points. For example, quartz melts below 1670 degrees Celsius. Now, so did you know that gallium's melting point is roughly 29.7%? This temperature is slightly higher than the room temperature and lower than the body temperature. Therefore, it will melt when you hold it because of the warmth of your hand and will be back to its solidified form when you remove it. Gallium never existed in nature as pure element, but rather they are found in trace amounts in some minerals. Okay. So here are the mineral groups that are determined by the chemical composition. So actually, it has 9 groups of minerals. So first one is elements. So most of the elements have, or most of the minerals here are composed of only one element. Having knowledge about elements enables scientists to identify bonding possibilities and compounds that can be created. For example, aurum, copper, silver, ano pa ba? Sodium, potassium. So these are example of elements. So, example of minerals that exist commonly in elemental form or in element form are copper, gold, silver, and sulfur. Next one is the sulfides. So when we say sulfides class, so they are joined by sulfur. So minerals under this group are composed of a metal that is joined by sulfur. From the word sulfide. So metallic cluster is the characteristic that distinguish them. Example, cinnabar and pyrite. So it has a metallic luster. Next one is halides. So these are nonmetals which consist of chlorine, fluorine, bromine, and iodine as their main chemical constituent. So we have here fluorite, which is a type of mineral, halite and diabolite. Next one is oxygen and hydroxide, or oxides. Get oxygen, oxides and hydroxides. So these are mineral groups that are composed of more metals with oxygen, water, or hydroxyl group. So we have cuprite and hematite. Next one is nitrates, carbonates, and borates. So it is formed when a metal is combined with carbon, nitrogen, and boron. Example are malachite, nitrotin, and borax. Next one is the sulfates. Now sulfates are composed of one or more metal that are combined with a sulfate compound, or they are combined with a sulfate. So these are metals that are combined with a sulfate compound. Example, we have here anhydride. Now next one is chromates, molybdate, and tungstate. So chromate, molybdate, or tungstate substituted the place of sulfate group. These minerals are usually brightly colored, brittle, and dense. Example, wolfenite and scheelite. Next one is the phosphate, arsenates, and vanadates. So one or more metal is combined by phosphate, arsenates, and vanadates. Example, apatite, lazulite, and vanadinite. Last one is silicate. So this is the largest mineral group. Minerals under this group have different amounts of silicon and oxygen. So example, dioptase and labradorite. Okay. So we have here analysis of the composition of the crystal structure of minerals. So in the laboratory, the composition and crystal structure of minerals can be analyzed through chemical and instrumental analysis. Chemical composition is investigated using wet chemical analysis and several spectroscopic techniques. So the wet chemical analysis involves dissolving a mineral in an acid and analyzing the solution. An acid is usually hydrochloric acid. If a bubble is evident, after putting drops of acid, it indicates that carbonate mineral such as calcite and dolomite is present. So the table below shows the reaction of common carbonate minerals to acid. So we have here, if you put a diamond in an acid, it will never be dissolved. Intense heat is the only thing that can destroy a diamond. So these are some of the reactions of carbonate minerals to acid. So you can just read it. Now, since we are done with the wet chemical analysis, let us proceed to the spectroscopic techniques. Spectroscopic techniques involve quantitative analysis. So it involves number analysis, or analyzing the data coming from mineral components. Spectroscopic techniques involves quantitative analysis of mineral components depending on the light absorbance of the compounds. This tests the sample's interactions with electromagnetic radiation to determine its structural and chemical properties. The types of spectroscopic techniques are the following. First one is the atomic absorption spectroscopy, or AAS. So it uses a controlled flame to separate the components of a sample and monochromator linked to a detector to search for wavelengths of light that are absorbed by the sample. This technique identified the concentration of mineral in a sample. So basta atomic absorption spectroscopy, it uses controlled flame. Now the inductively coupled plasma spectroscopy, it uses argon gas to move the sample vapor into chamber under high vacuum where both the sample and the gas are heated for the elements to give off a characteristic wavelength of light. This technique is able to trace and identify almost all the minerals. So, kini siya technique class is able to identify and trace almost all the mineral present in the sample. So, inductively coupled plasma or ICP spectroscopy uses argon gas. Now, the next one is the X-ray fluorescence or XRF spectroscopy, which uses a high voltage electrons towards a metal target to produce a specific wavelength X-ray beam that hits the sample. Comparing the sample intensifies so that the standard can be used to calculate the concentration of elements present in the mineral. This technique will give an analyst a real-time rock analysis, and this is more convenient and efficient than the older technique, which takes weeks before analysis is presented. So, the X-ray fluorescence uses a high voltage electrons. Now, next one is X-ray diffraction spectroscopy or XRD, which is a technique that only applies to pure amorphous or crystalline substance. When we say pure amorphous or crystalline, ito yung mga minerals which are in crystal formation. So, it is used to study the structure of the crystals, and this process is done by firing an X-ray beam. Kung kanina, it uses a high voltage, or the XRF uses a high voltage electron, the XRD naman uses an X-ray beam at a finely ground sample at different angle. Then reflected of diffracted rays can be used to compute for the dimension of the unit cell. This technique is used to obtain information from non-crystalline substances, particularly most minerals. Okay. Alright, so let us go over to the rock-forming minerals. So the common rock-forming minerals are quartz, feldspar, mica, pyroxene, amphibole, and olivine. So all of the following are silicate minerals. So that means majority of its components are silicon and oxygen, except for quartz are mineral groups. Now the quartz has a composition of SiO2. So it is a glass-like hard substance with white streak. It has a most hardness of 7, which makes the quartz grains resist scratching of nail or a pocket knife. Pure quartz is also known as rock crystals, that is colorless and transparent. Trace amounts of impurities cause colored varieties of quartz. So, quartz can occur as amethyst, which has purple violet, citrine, yellow, smoky or cairngorm, brown, morion, black, rose, pink, sapphire, quartz, blue, and milky, which is a semi-translucent white. The grains of quartz in general are irregular in shape and exhibit conchoidal fracture. Next one is feldspar. So it has a chemical composition of this one. So where X is potassium and calcium for Ca or sodium. So it is quite hard with a most hardness of 6. It is a light colored mineral that is usually white but can also exist in lighter shades of red or green. It has a glassy luster. In rocks, feldspar form rectangular crystals that break along flat faces. So we have here two kinds of feldspar. First one is plagioclase feldspar, which is the most common mineral in igneous rock. Most plagioclase appear frosty white to dark green. Using a hand lens, one can often see the stairs tip like cleavage and possible striations of parallel grooves. Diba? Masyag na ay mga kung padulungan na matipak na fragments of rocks. Next type of feldspar is potassium feldspar. So they commonly occurs as slightly pinkish grains. Unlike plagioclase, it does not contain striations on its cleavage. It has two cleavage planes at both 90 degrees. Mica. So mica is in a group of hydrous potassium, aluminum silicate minerals. Mica, so ibig sabihin aning hydrous potassium plus kana more good siya liquefied form of potassium and aluminum silicate minerals. More gatubig ba na potassium and aluminum silicate minerals. Now mica is soft, which with hardness ranging from 2 to 2.5. It is easily identified by its perfect cleavage, reducing it to thin, smooth flakes. Its luster is responsible for the flashes of light in rocks, such as granite and slate. We have here different kind of mica. We have Muscovite mica, so which occurs as white, shiny, and silver mineral. So it has a purely to vitreous luster, white streak, and often shades into tiny flakes when scratched. So dahil siya mga pulpog. Biotite mica is a dark green or dark brown, shiny, and often occurs in small hexagonal crystals. It has a vitreous luster, flaky habit, and white to gray streak. Biotite sheets are elastic when bent. So biotite minerals are elastic when bent. More siya flexible siya na pagka-minerals. Next type of mineral is pyroxene. Pyroxene minerals have general composition of this one where X is calcium or magnesium and Y is either magnesium iron or aluminum. So it occurs as short, stubby, black to dark crystals, dark green crystals. Although the other colors may occur, so it has a glassy luster with streaks of white, light green, or light brown. So it has a good cleavage on two directions, both at almost 90 degrees, and cleavage surfaces are often hard to see in a regular rock sample. Augite is the most common mineral of this group. Amphibold has general formula of Yan. And is a dark color with most hardness ranging from 5 to 6. It is opaque and has a glassy luster. When we say opaque glass, that means light cannot penetrate the internal structure, or it is impenetrable by light. So it occurs as long and slender crystals. It has good cleavage in two directions, approximately 60 degrees and 120 degrees, and therefore has a stair-step appearance under a hand lens. Hornblende is the most common amphibole. Next one is olivine. Ganda na yung kulay ng olivine. So, olivine is a silicate mineral with a general chemical composition of magnesium, iron, silicate. But calcium, manganese, and nickel can be substituted for magnesium and iron. So it occurs as small, light green, glassy crystals. It is commonly used in the gemstone, kaya pala, industry as peridot. So olivine is commonly used in the gemstone industry as peridot. It is a glassy looking and transparent substance that is almost as hard as quartz. Its sugary or saccharoidal texture and olive green color make it distinctive from other rock-forming minerals. So from the word itself, olivine, so kaya nga meron siyang sugary or saccharoidal structure and olive green color, which makes it distinctive from other rock-forming minerals. Okay, so these are the physical properties of some chemical or some common minerals. So for gold, gold is a type of mineral which has a yellow color, and then the straight color is actually golden yellow, and luster, metallic. So ang luster man iyang kahamison. Unsa siya kahamis? Unsay dating niya? So metallic luster. Now the corundum, its color is usually blue for sapphire and then red for ruby. Straight color, white. Luster, vitreous to adamantine. Graphite, dark gray to black. Now, dark gray, the same color, kung ano yung kulay niya physically, the same also goes with its straight color, which is from dark gray to black. Tapos, it has dull metallic luster. Fluorite, colorless. So, color can be colorless, purple, green, white, yellow, pink, red, blue, and black. For the straight color, it has only one color, which is white. Luster, vitreous. Now, the next or the last mineral is galena. So, galena has actually a lead gray color, and for the straight color, it has the same color physically, which is also lead gray. And then for the luster, it has metallic luster. So that ends the discussion for lesson 6.1, which is all about rock forming minerals. So taas-taas siya, so laban lang jud tani. Now the next discussion will be all about igneous rock.